So I'll just get started then. Let me start the slideshow. Okay, so we all depend on the power grid for everything that we do, including right now. Um, but the power grid is aging, and it's extremely complex. And we've been adding a lot of new sources like solar and wind that are very intermittent. Now, at the same time, we're going through a period of electrification where we're converting so many things to run on electricity. And also, we're ramping up artificial intelligence data centers, which are putting additional burden on the grid. So let's take a look at some of the problems that we're facing. So this is a map of the PJM region. I'm going to see if I can move that. Okay. So PJM stands for Pennsylvania, New Jersey, and Maryland. And over the years, it was expanded to include Ohio and Virginia and parts of Kentucky, but they still call it the PJM region. But this is pretty typical of what's going on. They expect a 40% increase in electricity consumption over the next 16 years. And it's largely due to data centers in Pennsylvania and data centers in Virginia. So this is a map of the power grid. As you can see, it's extremely complex and it's interconnected. So when it's interconnected, that's a good thing because different regions can help each other out. But on the other hand, it's also a bad thing because sometimes if there's a disruption, it can pull down uh, neighboring neighboring regions. Um, so the Department of Energy is working on this. They have a program that will add 13 gigawatts of grid capacity. Uh, and even individual businesses and homeowners are taking steps such as adding Tesla power walls. So each power wall battery can store 13 and a half kilowatt hours, about enough to power a typical home for a day. And so if this house, if the grid in the area were to go down, it could run for 2 days on those two Tesla Powerballs. Another strategy that's being tried is advanced power flow control, and it redirects power from congested lines to underused lines. So there's a diagram below that. On the left, it shows one line is overloaded at 105%, while the other two are at 40% and 28%. And so if you do this improved power control, you can get them all evenly loaded at about 98%, and you end up with about 1,800 megawatts of additional uh, capacity. So just by managing the flow of power better, you can increase the overall power capacity of the grid. Another thing that you can do is you can bundle together small power plants. So you can bundle together photovoltaic plants with wind turbines, energy storage devices, which are batteries, electric vehicles, which have batteries in them, and demand response is where people cut back on their power consumption. Cutting back on the power consumption has the same effect as increasing supply, so it can be counted as a supply. But anyway, if you bundle these together and coordinate them, essentially what you have is a virtual power plant. Another term that you hear frequently is distributed energy resources. And that's where you have a lot of small sources of power generation and storage. So in the old days, uh, you had a few large central power plants, and the power just radiated outward like the spokes on a wheel. And that was a very easy system to manage because if you just have a few large power plants, you just have a much lower level of complexity. But now you have literally thousands of individual power producers, everything from solar panels on people's roofs to uh, small power plants at hospitals and universities and so on. So it's just become a much more complicated system to manage. Um, Another strategy is what's called a microgrid. So if you have an area um, or a site which has a collection of power generation, energy storage, and ability to isolate from the grid, which is basically having controls that are able to manage that, then you can set up your own independent power grid that would continue to operate even if the main grid goes down. So places that could do this would be, you know, military bases, hospitals, um, uh, industrial facilities, um, anything which has, you know, sufficient power generation on site that it could operate on its own. So this, of course, is wonderful for reliability because then you have the power grid 99% of the time, and the 1% of the time when the main power grid isn't working, you have your own on-site power grid. So here's part of the problem. A data center consumes 10 to 50 times more energy per square foot than an office building. And so, you know, adding a few data centers is puts much more demand on the grid than just adding a few office buildings. And artificial intelligence, because there's so many more calculations involved, consumes much more power than your standard uh, data center operations. So EPRI, which is the Electric Power Research Institute, they estimate that data centers could be 50% of the electric load in Virginia by 2030. And 2030 is just 5 years away. And it takes a long time to build things in the power industry. And so they're building plants and reactivating old plants as fast as they possibly can. And it's still a race against time to try to get all that capacity online by 2030. So I mentioned before, you know, smart grids, how you can manage the existing grid much better by adding a lot more information technology. That's basically what the smart grid is. Uh, but that creates its own problems because the smarter the grid gets, that is, the more dependent the grid is on information technology, then it starts to become more vulnerable to cyber attacks. And so a common attack on smart grids is false data injection attacks. You just flood them with so much incorrect data that it just overwhelms the system. But on the other hand, artificial intelligence has a lot of benefits for the grid. It can operate the grid more efficiently, detect faults and respond to faults more quickly, And it can also defend against cyber attacks. And it mentions in the lower right-hand corner also employee training. And training is a very big thing in the power industry. And of course, artificial intelligence training programs can really help with that. And it's not just enough to build power plants because you have to get the natural gas to the power plants. Many of these power plants are fueled by natural gas, and so the pipeline capacity is not kept up either. So at the same time they're building power plants, they also have to build more natural gas pipelines. Now, another thing that's going on is that the workforce in the power industry is aging. Uh, Utility jobs tend to be nice, steady, long-term jobs, and so people stay there, and they stay there until their retirement. But there's a wave of retirement coming up. Half of the workforce will retire in the next 5 to 10 years. And the specialized knowledge that they have is very difficult to replace. So the American Society for Civil Engineers gives our energy infrastructure a D plus and says almost $2 trillion of upgrades is needed. Now, of course, the $2 trillion of upgrades, that's not all going to happen, uh, but it just shows you the depth of the problem and how much money we have to spend on repairing and upgrading the grid. Okay, the regional transmission organizations, they predict explosive growth. So this shows all the regional uh, organizations in the US. You see the PGM one that I mentioned earlier, and this map shows the other ones. So 40% of data centers could face power restrictions in a few years if the power supplies don't keep pace. And so obviously this could have a very severe impact on the economy if we don't have enough power for our data centers and if we don't have enough power in general. Uh, and if our grid had more capacity, we would better be able to move cheaper electricity around to where it's needed. So we have to improve not just the quality, but also the quantity of grid capacity. So Deloitte estimates AI data center power demand will grow by a factor of 30 over the next 10 years. So you see that, the growth is just explosive. So they're bringing back nuclear reactors. We went 40 years building only one or two nuclear reactors, and now they'd like to have 10 large nuclear reactors under construction by 2030. So the good news, if you're looking for a power engineering job, it could double to 1.5 million power engineering jobs, uh, but it could be difficult to find candidates uh, because it takes a lot of specialized training, and a lot of people don't have the specialized training. And part of the problem is that young people don't choose power generation as a career. It's not something they think of. It's not something that they're familiar with. And so we really have to get the word out to the young people that, hey, this is a great career. There's a lot of opportunities and a lot of growth in the future. And another part of the problem is a lot of the things that we need, like the industrial transformers, are made outside the US. Many of them are made in Asia, and there's very long lead time from ordering the transformer until it arrives at the site. And there's also like a 2-year backlog because everyone is doing the same thing at the same time, increasing their power supplies, and they just can't get the transformers fast enough. And so 70% of the transmission lines and transformers need upgrades. And unfortunately, it's going to drive up electricity prices because all this investment and upgrades and supply shortages and high demand, it's all going to drive the prices up. So, customers are accustomed to highly reliable power. They don't realize the situation that we're in. We need to make sufficient or significant investment in the power grid infrastructure, but we also need to make significant investment in workforce training and recruitment because it's not just equipment. We also need people to keep the power grid running. Okay, so these are my sources and contact information. So